electromagnetic induction. Here is a solenoid and here is a meter or galvanometer. You can connect it. Galvanometer is a device to detect the current as like a meter, but the galvanometer is more sensitive. Even a small amount of current can be detected. And here is a magnet, and here the north pole is facing toward the solenoid right now, and it has magnetic field lines from north to south. And when you move the magnet into the solenoid, the magnetic field lines are being cut by the solenoid. The magnetic field lines are being cut by the solenoid, induces EMF. So when the magnet is moved into the solenoid, magnetic field lines are being cut by the coil or the solenoid, induces EMF, and which causes induced current. So here you cannot say it produces, it creates. This word is very important. Induced voltage, induced current. Sometimes you can write EMF or voltage or potential difference. Induced potential difference causes induced current. As long as you move the magnet in and out, the magnetic field lines are being cut, or you can say the magnetic field lines are being changed. As you move the magnet in and out, magnetic field lines are being changed by the coil or the solenoid, induces EMF, and it causes induced current. In figure 1, a magnet is moving into the solenoid. Into the solenoid means to the left. Now you can see the ammeter or the galvanometer, the needle deflects to the right momentarily. A momentary right deflection, which means it goes to the right and get back to zero. It's a momentary deflection. It may show you 0.5 ampere or 1 ampere, whatever, when the magnet is moving into the solenoid. It moves to the right momentarily. And now my question is the second diagram. What if the magnet is moving out of the solenoid? When you remove the magnet out of the solenoid, the deflection will be in the opposite direction to the left, momentary deflection. It will move to the left and back to zero. This deflection is called momentary left deflection. It deflects to the left momentarily. So this word, this momentarily, this word is important. So as long as you move in and out, the deflection, you can see the deflection to the right and left momentarily. Now if you want to make a deflection to high, what we have to do? Now before the deflection, right deflection to 1 ampere, now I want it to 2 ampere. So what changes can be to increase the amount of current? It's very easy, simple, that you have to move magnet faster. Move the magnet faster. Another one, increase number of turns of the coil. Number of turns of the coil. and another one, increase the area of the coil. Increase the area of the coil. So here you can increase the amount of induced current as you move the magnet faster in and out, in and out. The same thing happen if you move the solenoid and keep the magnet constant and move the solenoid in and out. The same magnetic field lines are being cut by the solenoid, induces EMF, causes induced current. The same thing happens as you increase the speed and number of turns and area of the coil. You increase so that your magnitude of EMF. Magnitude means the amount, a number. For example, 1 ampere is increased to 2 ampere. This is the magnitude. Magnitude of EMF is increased. Here the resistance of the coil does not affect EMF, voltage, potential difference. It will not affect the EMF, potential difference and the current. Only the speed of the coil movement or the magnet movement, or you can move both mutually. Number of turns increases and the area of the coil, the thickness of the wire increased. So you can increase the EMF, amount of EMF or the magnitude of EMF. A voltage time graph. Here is a solenoid and the magnet, and speed of magnet is here, for example 1 meter per second I gave you. As it moves with the speed of 1 meter per second, it produces 5 voltage positive and here 5 voltage negative. We get the wave like this. Now we are going to draw the wave if the speed of the magnet movement is 2 meter per second, which is almost doubled. Speed is doubled. If speed is doubled, EMF, the magnitude of EMF is also doubled. Before it was 5 volts. Before it was 5 volts. Now it will be 10 volts because the speed is double. Here we have as another one factor to be noticed, that is the frequency. As you are increase the speed, the frequency in the given time with respect to the time is doubled also. Here we have one wave, here from here to here one wave. If you see the unit of time here, 1 2 3 4 units, it takes 4 units for one wave. Now here in these 4 units, 1 2 3 4, there will be two waves. We have to draw two waves, which means here in this space one wave and this space another one wave. So here we are going to draw one complete wave, and also the voltage is doubled. So the graph looks like this. Here we have to draw the half wave. So here you take a point and connect like this. Here is a crest and 10 volt crest, positive side, and here the negative side, put a point so it will be easier to draw a wave like this. Now we have drawn one wave. Here the amplitude of the wave is increased. It denotes, this amplitude denotes the maximum voltage, 10 volts now. And also the frequency is doubled. Previously at the same unit of time, in this unit there was a half wave. Now in the same unit there is a full wave. And then another one wave can be drawn for the practice, or even this wave is also enough for just for the practice. I can draw in this one unit Before it was full wave in the 2 units. Here we have the 2 units. We need to draw one complete wave. Before it was one half wave. Now in this unit we are going to draw full wave. So here is a half. Draw one crest, and another half. Draw one trough. One complete wave. Here is the another graph, same voltage time graph, but here we keep the speed of magnet is constant, but we increase the number of turns of the coil. So for the first graph, if you see, as you are moving with the speed of 1 meter per second in and out, the induced EMF is produced, and we draw the graph. The maximum voltage is here 5 volt and the negative 5 volt. The maximum and maximum 5, negative, minus 5 volts. What if you increase the number of turns? Number of turns are here doubled. If the number of turns are doubled, voltage is also doubled. Before it was 5 volt, now it will be 10 volts. But what about the frequency? Frequency will be constant. Unlike speed, when we increase the speed of the magnet movement, the frequency also double, as well as the voltage. But here the voltage, only the voltage will be changed, but the frequency, the number of waves are the same. So how will you draw here? Here before it was 5 volts, now it is going to be 10 volts. So here is the range, and here, so within this point we are going to draw one complete wave. So first you split into two equal division. Here is the center region, and in this space we draw one crest, and in this space we draw a trough. So you draw a crest. Now it is changed to 10 volt, the maximum, and here the minimum. This middle is here. So draw a trough, right? So here is minus 10 volts. So the frequency of the wave is the same, constant, because the speed of the movement of the magnet is the same, constant. So the frequency will be remains the same, but the voltage is doubled. Here is a question 1. Describe the motion of the magnet. Here is a voltage time graph. You can see the waveforms. Here you can see the maximum voltage, and the voltage is being reduced. Here it is the lower voltage. The voltage is changing, decreasing. That means the motion of the magnet. Speed of the magnet decreases. Speed of the magnet decreases. So what are the observations here? What are the observations? 1. Frequency of the wave decreases, and second observation, amplitude of the wave decreases. So these are the two observations from the graph. Here is the amplitude, amplitude, amplitude. The amplitude is changing continuously. And frequency, here 2 units for one wave. Here 2, 3, 4 units for the another one wave. Here 1, 2, 3, 4, 5, 6, 6 units. Time taken 6 units for the another one wave. So the frequency of the wave also changes, that decreases. Question 2. The graph shows the output of an AC generator. Here is the voltage and time graph. The coil in the generator rotates 20 times in 1 second. If the speed of rotation of the coil steadily increases, which graph best shows how the output voltage changes? Now the speed increases steadily. Speed increases, frequency increases, voltage increases. If you see here, 1 volt, negative 1 volt. As we are increasing the speed, voltage must be increased. So if you see the option A, B, voltage doesn't change. Voltage doesn't change. Voltage is same. So these two options are wrong. Here are the another possible options C and D, and we have to select the right one. And if you see here, the voltage increases. If we are increasing the speed V, voltage increases here. So that is correct. But what about the frequency? Frequency is the same. Frequency is reduced, decreases. In this case 3, frequency reduces. So the option is wrong. Here you can see the frequency at this point. Here 0.05, but here the frequency is increased. Here at this 0.1 second, here is 0.1 second. Here you can see two waves. Here is one and here is two waves, but here you can see 1, 2, 2 half. 2.5 waves are there in the given time, in the given 0.10 seconds. So here frequency also is higher, voltage also higher. So the option D is right. Faraday's law. Magnitude of induced EMF is directly proportional to the rate at which magnetic field lines are cut by the conductor or a coil or a solenoid. Here the magnitude of induced EMF. For example, induced EMF is 2 volts, is directly proportional to rate at which magnetic field lines are cut. If you want to get 4 volt, the rate at which magnetic field lines are cut should increase. If it cuts, the rate means the speed. If you increase the speed, you can increase the voltage as well as the frequency. Only for the speed. If you increase the speed, voltage increases, at the same time frequency also increases. If you increase the number of turns, voltage increases, frequency remains the same. If you increase the area of the coil, voltage increases, frequency remains same.